My name is Clay from OpenC3, and in this video we'll be talking about the MAVLink plugin that I wrote for OpenC3 Cosmos and discussing the development details, installation, and how to use it for simulations and real drones. So MAVLink is a messaging protocol. It's the micro air vehicle communication protocol, and it's a very effective way to communicate between drones or rovers or anything that supports MAVLink v2 with other devices. Maybe it's a controller, maybe it's a software, whatever it might be. Depending on the vendor, we'll have different types of messages that it will send, but generally speaking, there is a common set of messages included in the common.xml file, like this one. So the common XML has a pretty sizable list of common commands, common telemetry that is used across the variety of hardware that uses MAVLink. And then this is a great starting place to implement some of the messaging protocols. And then there are supersets like ArduPilot Mega or different, depending on the vendor, different types of messages that go on top of this. Overall, MAVLink has a lot of commands and telemetry that is well defined and using these packet formats. In this video, we'll be using MAVLink version 2. And in this packet format, we can see some of the common headers that are used across of all the different commands and telemetry, and then all the different information that is within that packet. The MAVLink plugin that I wrote for Cosmos is publicly available on OpenC3 Cosmos MAVLink on github.com, and it's also available on the App Store, which we will go over soon. But just kind of going over the high-level details of how this plugin was written, we can take a look at this repo, where within the helpers, I have the various XML files that I use as a basis for building out these the command telemetry database. I used common XML, minimal XML, standard XML, some of the base XML files for the MAVLink version 2 messages, as well as some of the other vendors like ArduPilot Mega. We have Icaros, QPilot, and so on and so forth to build out this more larger set of commands and telemetry so that we have this very generic plugin that can work with many vendors. After downloading all those XML files, I effectively created a script here, a Ruby script, to convert all those different messages from MAVLink format, the XML files, to something that Cosmos understands and makes it easier for us to use. So running the script, it goes over those XML files and converts them into the Cosmos format. That leads us to the command and telemetry database found here in the command and telemetry portion of our code, such that all the different commands and telemetry are just defined, the commands in one file and telemetry in another file. There are 170 commands and 321 telemetry packets defined. So hopefully for whatever project that you may be working on or using this for, all those are already predefined for you. A lot of these will also have the conveniences of Cosmos features like units defined, states defined, so that you'll have an easier time integrating with our software and using it for your missions. Going into some detail about the architecture that we have here. So we have our vehicle, which might be some kind of flight controller, or it could be a simulation running on Gazebo. And then we have it connected to Cosmos either via TCP or UDP. The plugin will allow for both, and then you can use it however you wish. And then we have a MAVLink protocol.py file, which is going to act as the interface that is parsing in the raw bytes that are coming in from the actual device to Cosmos. And then in Cosmos, we're using JSON accessors to parse out the MAVLink protocol and then parsing it into Cosmos formats. This is the telemetry flow where we have vehicle to Cosmos. Commanding is just going to be the exact opposite, moving the reverse direction. We have command packets that we build in Cosmos using the MAVLink protocol to send out the bytes using TCP or UDP, and then our vehicle will accept that. So when we are receiving data from our vehicle or our simulator, we're basically looking for the sync byte. The sync byte is going to be 0xFD as defined by the MAVLink format. And then we're continuously looking for data until we find that. Once we find the sync byte, we'll grab the payload length indicator to see how long this payload is going to be. We'll grab that and then we'll wait until we have the entire packet's worth of data. Because we're leveraging PyMavLink, CRC checks and ensuring that the packet is valid is all assured for us from the PyMavLink library. The commanding interface works just in the opposite direction, where we receive JSON into the interface, and then we send out binary MAVLink version 2 packets out. We have some custom code here for special handling of command long parameters, making sure that we fill it in with the correct parameter numbers. And then we do some autofilling of missing fields with type appropriate defaults. And at the end, we make sure to increment the sequence number so that we're continuously counting up these sequences. So now let's see it in action. So first, I'll be demonstrating showing how we can use the simulator to connect to Cosmos, and then we'll demonstrate on a real live drone. So first, starting off with the simulator, I have Cosmos deployed here. One difference here is that I'm going to have this UDP port open. That's the MAVLink port for Cosmos to receive from our PX4 simulator. And in this example, I'm just going to be using UDP as that was the suggested protocol for the Gazebo simulator. I'm going to start a Gazebo X500. It's a quadcopter simulator using PX4 software in the loop. And this is just from the PX4 autopilot. And then what I'm going to do is that I'm going to start a stream using MAVLink start -x-u 14560 and then -o 14552, just some ports that I'm opening for a UDP interface, the 14552 being the one that we'll be sending out to Cosmos. And then I will start that. And then I'm also setting some defaults telemetry rates for altitude and attitude and all the different things that's coming out. I'm just setting them to 1 Hertz so that for viewing this, it's a little bit more intuitive to look at. And of course, these can be sent out as Cosmos commands. I'm just doing it here just to kind of show some of the more familiar workflows. At this time, we should now be able to open up the Gazebo simulator, and there should be a quadcopter ready for us to test with. With a vanilla Cosmos deployment and nothing installed right now, I'm going to go into the admin console and I'm going to go to the browse plugins button here. And then I'm going to search for the MAVLink plugin that is ready for me to install. I'm going to hit install. And then the same ports that we had defined previously on the command line for MAVLink, the PX4 simulator. The right port I'm setting to 14560, read port 14552, and then the protocol type to UDP. Of course, these port numbers will be different depending on what your custom setup looks like. I'm going to hit install there, and then I'm going to give that 15 seconds or so to install. And then once it's installed, we should now be seeing telemetry. So this is fantastic. We have now the simulator integrated with Cosmos. We're receiving telemetry. If I go to the Telem Packets tab, we can see what telemetry we're receiving. So flipping through the pages here, looks like we're getting altitude information, attitude quaternion. I previously set everything to 1 Hertz, so we're seeing that reflected here. And then as we flip through the pages, we'll see different types of packets that we're receiving. Within Script Runner, I have staged a script called Survey Mission, which will take advantage of all those different commands and telemetry that we have in Cosmos, and then run through this entire script and be able to upload a mission and then start our mission on our drone. So I'm going to hit start here. And this will work through the process of uploading our mission to our drone, and it's going to sequentially go do that and make sure that the drone is fully aware of the mission. And it's going to prompt us, hey, make sure that the area is safe and clear for us to arm the mission. What's fantastic about this setup is that not only can we use the simulator, but we can also use something like QGroundControl, a tool that you may be more familiar with in these drone operations, so that you can use Cosmos in conjunction with QGroundControl to fully rehearse your mission and use all the tools that you want at your disposal. So at this point, I can launch it from QGroundControl, or I will continue on Cosmos to go ahead and approve this survey mission. And the hazardous command to component arm is approved. So now that the command has gone through, we can see on QGroundControl the sim is moving out, it is flying, and it is carrying out our mission for us. Over in Cosmos, then we can be watching the live telemetry that's coming in. So we can take a look at attitude information, we can take a look at the battery information. I have a variety of screens that I have pre-prepared here, but these are very easy to make. So some of the other examples, we're receiving attitude quaternion data, so we can take a look at what information we're getting there. Looks like we are on our way back on this mission, so we can watch this all live on QGroundControl coming back into position, back into our original starting position. Back in script runner, we are close to coming back to the end of the mission, so we receive another hazardous command to disarm the vehicle, so that has been approved, and we have completed our mission, which is great because now I can go into execution status and I can view the entire log of what happened in this mission. So everything is repeatable, everything is fully logged, monitored, so that you can repeat these missions as many times as you want, so that when it goes onto the real vehicle, it is fully rehearsed and fully trained. For the actual drone, I'm working with a Pixhawk 6C mini flight controller, and this is a great way for us to be able to validate and test out our integration to make sure all the messages that we're receiving and sending are all correct. In the plugin.txt file, under the TCP-based Python MAVLink protocol definition, we'll see 3 layers here. We have the interface, which is going to be the primary interface that we interact with. This is going to be receiving the data coming from our MAVLink transmitter or whatever source that might be. The second layer is a router. This router is going to be the TCP/IP server, and it's going to be actually opening up port 2977 inside the operator container inside Cosmos, such that all the different telemetry that we're receiving can be sent out and commands can be received in. And then the third layer is going to be the interface that reads and writes from 2977, and it's going to actually use that MAVLink protocol to then parse the messages and save them onto Cosmos. What the router allows us to do is that with having this external port that's open, other softwares and external systems like QGroundControl can be subscribing and listening to 2977 so that it can send commands to Cosmos for Cosmos to send it out to the actual flight controller. What this allows us to do is have a very seamless integration with external systems with Cosmos, and then also benefit from all the different advantages from Cosmos, like logging everything, monitoring all the commands coming in, and be able to be the centralized ground system as part of your setup. Because we have 2977 open as part of our system here, in the compose YAML for OpenC3 operator, we'll keep that 2977 port open for TCP/IP server. The process for installing the plugin is going to look quite similar. We're going to start off by going to the administration console, browse plugins, and then I'm going to look for the MAVLink plugin. And this time I will be using the TCP/IP protocol, so everything else will stay as is. And I'll go ahead and install. After 15 seconds or so, you should see this screen where we have the drone interface connected. In the raw interface, I still don't have the actual flight control sending any data, so that is still in the attempting stage. So propellers are off, and I'm going to go ahead and plug this in, turn it on. And then I have here a Radio Master Boxer transmitter, so I'm going to turn that on to get these two connected. All right, and the two are now connected, so I am receiving telemetry on the transmitter side. So we have the transmitter and the drone connected well together. So next, we want to establish the communication from our transmitter to our machine. So opening up our Bluetooth settings here, I do see the transmitter available, so I'm going to connect to that directly. And then I'm going to use the default pin 1234. And then I'm opening a bridge here, a serial bridge. And just briefly describing this, the bridge is supposed to be a very, very simple way to communicate the data into Cosmos. Effectively what this bridge is doing is that on my macOS device, the Docker containers can't communicate with my serial ports directly. So it's simply exposing the port, that's the write port and read port that is defined here, which is going to be the Bluetooth equivalent serial port. And then forwarding that to the TCP/IP server 2950, and that is where Cosmos will be listening to. So this way we're able to communicate and send data to Cosmos without worrying about the serial ports as much. But with that bridge up and running, we do have telemetry now coming in. We saw this communication connection success from our drone, and we are receiving data. So that means when I go into Packet Viewer, I can take a look at a variety of data here. So let's say I want to look at the attitude packet, and then I can see the data flowing in. If I pick up my drone here and start manipulating it, I will see these numbers drastically change. Again, there are 321 telemetry packets, so a lot to look at here. Of course, not every one is going to be applicable for every single drone, but this is just that superset of all the different commands and telemetry that's available. On the commanding side, we can actually send out commands directly. So for example, I don't have my propellers on, so I can mostly do this safely, but I can send the arm command, which will be a hazardous command.
Motors armed.
And then we'll see all those things spinning, and then you can definitely hear it more than see it. And then we'll go ahead and disarm
Motors
that.
disarmed.
And there we go. So we can kind of have this communication of all the drones. And then, of course, if you go into Telemetry Viewer, so maybe attitude is interesting here. So if I'm moving this around, we'll see those numbers drastically change. And then, of course, because we're leveraging Cosmos here, you will also be able to enter playback mode where you can start looking at historical data. So maybe I wanted to look at, I've only had this connected for a few minutes, but just like the last minute's worth of data, we can play back historical data to screen so that if you had a mission that you ran, you can play it all back in real time. So, and you can make this go at 5 times the speed, so you want to look at things moving more quickly. So all those missions that you ran or rehearsed, you can monitor them, review them, rewatch them, replay them, so that everything is successful. In a previous video, we also showed how if you have payloads integrated to your drone, so in this example, I have this flashlight, which can attach directly to our drone, like so, then we're able to control any of the payloads using all these MAVLink commands as well. In this example, it was a servo controller, so you can make it flash in and out, you can make it swivel up and down, and be able to manipulate your drone and all the payloads on it. Thank you again for watching this video. If you have any other questions, please let us know. Hope to see you at a future conference or at the Space Software Summit. Until next time.